name is Raymond, and I'm from Team Canada, and I'll be presenting problem number 16, sinking bubbles. So let's quickly go over the problem statement. When a container of liquid, for example water, oscillates vertically, it is possible that bubbles in the liquid move downwards instead of rising. Investigate this phenomenon. So let's look at several parameters that I believe will affect this motion. So first off, there's going to be an oscillation frequency, the oscillation amplitude, and also the density of fluid, all three of which will affect whether or not we observe the phenomenon of sinking bubbles. So here's a quick overview of my presentation. So first, I'll go over a quick reproduction of the phenomenon, followed by my experimental setup and how I control various parameters, and while also varying others. Then I'll go over my theoretical model, which consists of looking at fluctuating volume, the equations of motion, followed by a brief numerical solution to create a graph. And then I'll look at various key parameter interactions as I discussed before, and then conclude with some other further insights and perhaps improvements on this experiment. Alright, so let's look at this phenomenon. So here you can see, so these three are the same videos, you can see the bubble, so you can see those green lines being drawn across the screen, and that just shows the bubble, the same bubble at different positions of time, and you can see that the bubble is sinking rather than floating as we normally expect a bubble to do. So now I'll go into my experimental setup. So first we have a dark backdrop, which we'll be using to help better observe the bubbles. So we have a clear oscillating cylinder, which is placed upon a subwoofer, which will provide the oscillations. Then this is connected to an amplifier, which is connected to a signal generator to produce sine waves that will oscillate our subwoofer. Then we actually have a straw, which is used. So we're going to be pumping bubbles into the container to produce bubbles at a fixed height. And then because of this, we have to release pressure, which is why we have the straw. Next, we'll be recording all of this with a 960 fps high-speed camera. Alright, so here's a picture of my experimental setup. So you can see the dark backdrop, the signal generator, amplifier, the stopper which is used to seal the container, and all the other components as I mentioned previously in that diagram. And in the picture on the right, you can see a close-up image which shows the air tube, which is used to produce the bubbles. So in terms of measurement, so one form of measurement we use is with tracker. And here you can see it's tracking one of the bubbles, and you can see the graph on the right, which is going to be the vertical position as a function of time, and you can see that the bubble is slowly sinking. So in terms of amplitude control, with a subwoofer, when you're changing the frequency, the amplitude will inevitably change as well. So if we want to vary amplitude or vary frequency without varying amplitude, it requires us to slowly go through many different settings on our signal generator in order to find points at which certain frequencies at which the amplitude is fixed, which is what we did for our experiment. Next, in terms of measurement methods, so for lots of our data, we're going to be analyzing the critical height at which sinking bubbles will occur. And to do this, we're going to be measuring the depth of the straw which produces the bubbles using calipers, and here are the dimensions, the relevant dimensions. So we have the container height, the container width, as well as the tube depth range, which is going to be from 0 to the height of the depth of my container. So now let's jump into my theoretical model for this problem. So first off, we have the fluctuating volume. So if we look at this bubble, you can see this is just a quick geometry. You can see all the variables here. And then we're going to be looking at the fluid pressure acting on the bubble. So here you can see the force of gravity, the pressure caused by the presence of the fluid around a specific small region dx, and then using Newton's second law with the first equation, and then integrating, we can get an expression for the pressure as a function of this oscillation, which is represented, as you can see on the bottom of the diagram, by a sine omega t. And when you take the second derivative of that to get acceleration, you'll get a omega squared sine omega t, which allows us to get that second equation. And then this finally allows us to get a pressure function, which is our third equation, from that force equation. Alright, so now let's look at how the bubble volume fluctuates with regards to time. So you can see we're going to be using the ideal gas law, so PV equals nRT, and we're going to be assuming a quasi-static and isothermal process. So in that case, we can do P external times the V of the bubble initially is going to be equal to Px pressure at a certain time multiplied by the volume of a bubble at a certain time. And doing this and using the previous expression for pressure, we can get the final equation at the bottom. So now here you can see the fluctuating bubble volume. So this is with an oscillation of our container, and you can see the bubble volume change over time. And this is a theoretical graph, and let's just compare it to a standard dotted line, which is just going to be your normal bubble volume, which is not going to change with regards to time. So now let's look into the equations of motion of this sinking bubble. So the main the main phenomenon that's occurring here that allows for the bubbles to sink is going to be the added mass, and that's caused by the displacement of a fluid. So when the bubble moves through the fluid, it's going to displace the fluid around it, and the displaced fluid must accelerate around the object. And we can treat this essentially as an added mass term, and this is here, which is a fairly common method for describing the sources. Phenomena, and you can see this source there, where we obtain the chi value for a sphere, since our bubbles are assumed to be spherical. And you can see the added mass, which is that dark blue ring around the mass. And for a sphere, we get that chi value is equal to 1 over 2. So now let's go over force analysis. Your standard Newton's second law of F equals Ma is not going to apply here because your mass is no longer constant. So therefore, we use F is equal to d more general, F is equal to dp dt, and then we can get you can get that second equation there. And then if we look at the balance of the forces, so first we have Fg, then we have your buoyancy force, finally followed by the force of the drag, which are the forces acting on this bubble. So now let's look at the governing equation. So here, once again, you can see the expression for the force balance, and you can see, so we can slowly expand this equation, so you can see that m naught term, which is representative of the added mass, and that's going to be changing with respect to time. So when you take the derivative of that, we have to apply the chain rule, which gives us that third equation. So now let's look at the drag coefficient. So first, we're going to have to look at the Reynolds number, and in maximum conditions, you have these parameters here, which allows us to calculate a Reynolds number of approximately 3.5 times 10 to the 4. And for this turbulent flow regime, we can assume that the drag coefficient of a sphere is going to be 0.47. And now what we're going to be doing is, since it's a fairly complicated motion, we're going to be dividing this motion into both a fast motion, which has a time average of 0, or a short period time average of 0, as well as a slow motion, which is illustrated for general motion. And we can divide it as such, as displayed here. And also you can see our equation for the quadratic drag on the top. So here's the fast motion. So this is actually derived by a paper from Sorokin. So here we followed some of the methods used for the harmonic oscillation, and we can derive several of the equations here. And similarly, we can do the same thing with a slow motion. So you have several constants. So you have a fairly complicated equation yet again. But you can see the constants down here. However, what we can actually get from these very complicated equations is a sinking condition. So if we assume that the acceleration of the slow motion is fairly small, which as implied by the name slow motion it is, we can get that second inequality over there, which describes a situation for which the bubbles will sink. So capital X naught is going to be the critical sinking depth, and you can see the equation for that over there, which can be solved by solving that inequality. And now for the sinking condition. So again, so we can actually simplify this equation down to x dot is equal, so the velocity of the bubble is going to be approximated as v, which is that term there, times x divided by x naught minus 1. And once again, you can see that x greater than x naught. So the positive direction is going to be going downwards. So for x greater than x naught, the bubbles will sink. And we can verify this equation by looking at the amplitude of 0, so your standard condition. So your x naught is going to be approaching infinity, and therefore your x dot is going to be less than 0, so your bubbles will rise as, once again, the positive axis is pointing down. So now let's use our numerical solution to start solving. So we use a Python to integrate those the differential equations as I showed earlier. And we get, so these are some parameters you can see here. So the blue line represents sinking, since again positive is going down. The green line represents unstable equilibrium in this system, and the red line just represents the floating bubble. So now let's compare this with our experiment. So you see here, so this is actually taken using, so that's a theoretical curve, and then we can plot our experimental curve on top of that, and you can see a fairly good fit with our analytical solution. So let's go over some key parameters. Alright, so first off, I'm going to be looking at the oscillation amplitude. So for that, we control the frequency, and then vary the voltage on our function generator in order to change the amplitude, and then measure this with tracker. So you can see here, the blue line represents the critical sinking depth, and to get each of these points, what we did is take the highest point at which we observe a bubble sink, and the lowest point at which we observe a bubble float, and average those 2 points, and the error bars represent that kind of range at which we would see the bubbles. And as we can see, there's a fairly good correlation with the theoretical curve of x naught. So you can see that we've divided this into several regions, so you can see where the bubble sinks, the bubble rises, and the maximum container depth, which is some of the limits of our system. Next, we have the varying oscillation frequency. Once again, you see the maximum depth, so you can see, once again, a fairly good fit with our data. You can see you can see the critical sinking depth again in the blue line, the region at which the bubble rises on the left, and the region at which the bubble sinks on the right. And next, so varying fluid density. So we can see not as good fit with this, but again, it still follows a general trend. So you see where the bubble rises, the bubble sinks, and the critical sinking depth. And much of this error can be explained to the fact that the bubble sizes are very hard to control. Even though we attempted to do that with a straw, it's going to be very hard to control, especially in different fluids where surface tensions are going to be different, density is going to be different, and in that way, the bubble properties are going to be different, and which means that density, which can explain some of the deviations we see when we plot density. So quickly summarizing the key parameters that we looked at. So we had a frequency, which has a negative correlation with the critical sinking depth. We have the amplitude, which also has a negative correlation with the sinking depth, as demonstrated by our graphs. And lastly, again, another negative correlation with density. So lastly, some further insight into this problem. So we used a chi value of half for a sphere. However, chi is going to be greater than half for a cylinder. So for a simulation, if we were to try to fit a greater chi value to adjust for potential compressions of our sphere, perhaps we would be able to obtain a better fit. Because for a higher chi value, perhaps we would see the sinking, since starting out to see some deviations at the end, perhaps that would correct for that. However, we were not able to do this with our experiment. And so in conclusion, we have a controlled experimental setup as demonstrated here. We controlled frequency, the height of where the bubbles form, the radius of the bubbles, and amplitude of oscillation. We varied several key parameters with fairly good experimental correlation, as you can see there. And then, here are my references that I use for this presentation. Thank you for listening, and
yes. So, why does the experiment and theory diverge over time on slide number 31?
Slide number 31.
Yes.
Give me one second. So as I kind of discussed this here. So for my chi value, I did approximate to half. So I can kind of expand why I believe. So chi is going to be greater than half. So we expect some compression of the bubble as it is oscillating, and that's going to change the chi value. So it's going to become slightly more cylindrical, which is going to divert the water around it.
We can discuss this in the discussion later. What algorithm did you use in order to solve your differential equation? You said you used Python, but what kind?
Yeah. So this is the ODN function from Python, which is it's a differential equation solver from the SciPy library.
Okay, and do you know what algorithm that uses?
It uses an algorithm from Fortran.
Okay.
I'm not exactly sure.
Do you have some numerical errors of your simulation? You have to estimate numerical errors from the simulation?
Estimated numerical errors? No, I don't. However, as you can see, there's fairly good.
Okay. Are there any fitted parameters in your graphs?
No.
Okay. Is it correct to model the system as an isothermal system?
Yes, we didn't. We don't observe. There's no.
You haven't seen any bubble string or some heat exchange? Or
no, we don't observe that. Since we don't.
Did you check that the beaker actually did a sinusoidal oscillation?
Yeah. So when we so what I did when I was calculating for trying to find amplitude with tracker, you actually do notice a sinusoidal curve with the whole system.
Okay. How was the bubble size determined in the experiment?
The bubble size was determined. So what we did is we took a picture of the bubble. We took a video of the bubbles being released from the straw and measuring that radius.
Okay. Did you do some error approximation on that?
What do you mean by an error?
Yeah. If you looked at multiple different sizes,
So generally, the bubble size was approximately constant. It was around 2.8 millimeters.
Are the bubbles traveling in some horizontal direction in your experiments?
Not much.
What was the Reynolds number?
The Reynolds number I showed was, I believe, 3.5 times 10 to the 4.
It's on. It's on.
Okay, great.
You can keep it right on. Hello, ladies and gentlemen. My name is Sondén, and I'm going to be opposing on the problem number 16, sinking bubbles. So, if we begin by the presentation summary. In the beginning, we got a lot of theory. They listed out the relevant parameters. And then they created a theory of motion, modeled by some of the pressure and the volume changes of the bubble in the liquid. Then also, by this theory, created a sinking condition, and then simulated the motion of the bubble. In the experiments, they had a quite rigorous experimental setup where they used a pump in order to create the bubbles. Here they also varied the amplitude and the frequency independently, which they think is important in order to check the significance of the theoretical model. They also tracked the bubble motion using a tracker, which is quite an accurate tool, and they had a good camera in order to see the effect occur. Yes, so now on to the conclusion of their presentation. They was able to observe the phenomenon, and they also created a theory of motion, and made simulation, and then they looked at the comparisons between the theory, and the theory fit quite nicely with the results presented. So, now to the test document. We thought some things we thought were great was the model and the theory fit quite nicely. They also had a quite rigorous, well-controlled setup. They also was able to create a theory of motion that wasn't using using some higher order of differential equations, which will perhaps such as Navier-Stokes equation, which will make it harder for them in order to see the actual effect of the system and look at some conditions. They would just be able to see how the motion would change. They also modeled a sinking condition, which was used in order to compare it with the results. Now to some things that I thought was lacking. They stated that the drag coefficient depends on Reynolds number, but then they said that it didn't affect by the Reynolds number, and they just fixed it to one value. And I would like to discuss why it isn't the case that it would change, since we have some oscillations in the liquid and the Reynolds number will change during the process. They also used a modeling method and they didn't know the numerical error of this modeling method, and they didn't know the algorithm, which could cause that we don't know the uncertainty of error in these numerical solutions. They did not also investigate the size of the bubbles and how that affects the motion of the bubble, because we have seen that it's quite important what the sizes of the bubble actually are in order to see the phenomenon to occur, and how added mass has an effect on that. And here, back again, they stated that Reynolds number changes with velocity, and here we have a system where the velocity of water changes a lot, but then they took and made an estimation that the drag coefficient was a constant, which it shouldn't be, since our Reynolds number are different throughout the process. So, I would like to begin by talking about why do the bubbles sink, and try to give a force diagram in order to let us understand the process more deeply. And I would also like to talk about how the Reynolds number actually changes with velocity, and since we think that it's really important in order to get the drag coefficient, is a central part of this phenomenon. And with that, I would like to invite the reporter up on stage, so we can begin.
Alright, sorry. Can I clarify about my numerical simulation?
with my question here.
Alright, sure.
Okay.
So why do the bubbles sink? So as
Okay.
I
Could we
described,
draw a diagram here?
I have a diagram of mine.
Oh, but
Just
perhaps I
save
think
some
it's,
time,
it would be great if we could do
Sorry, one second.
some modeling here. So we have a bubble for it.
Sure. Sorry, give me one second.
So we have a bubble here.
So,
Yes, but could you please draw the forces here so it will be easier for me to see it? Okay.
so you have gravity,
Okay.
G, you have the buoyancy, which is going up,
Okay.
and
how is this-
which way is the bubble moving?
The bubble, we can say it's moving down since.
Moving down. Okay,
Yeah.
so the drag is going to oppose that.
Yeah, exactly.
So that.
Yes. Okay. So why does the bubble sink? Because if you look at this
Right,
force
so-
diagram, we see that we have some drag and we have some buoyancy and some
So
gravitational force.
primarily, okay, so as you can see, so here, give me, sorry, so I guess just to clarify here. So in my discussion of the added mass, you can see that the rho here is going to be the density of water, which is going to be much greater than the density of air, which is going to be which is going to be the primary reason why.
But how does the added mass actually work?
The added mass essentially functions like.
Could you perhaps draw the added mass and how it changes throughout the size of the bubble? Yeah, exactly. Yeah, how does added mass change throughout the process? Will we have, if the bubble is small, will the added mass be, if we have two bubbles here?
Well, the added mass is just going to be proportional to the volume of the bubble.
Yeah, okay.
Which is, as I described earlier, is going to be sinusoidal.
Okay, so if we have a bubble that's moving up and down,
Sure.
the added mass, when it's the smallest, which is as it's moving down, yeah, the added mass is going to be smaller.
Yeah, because you can see in that equation that it's just going to be directly proportional to the water
And how does this connect to the bubbles moving down?
what do you mean by that?
Added mass, for instance.
Right, so so do you mean like why the bubbles seem to like accelerate almost as they go down?
exactly.
Okay, so that's going to be based because it's going to be volume. So that's going to be so if we compare the volumes of like the two larger yeah. So we're gonna have you're saying at the top you're gonna have a larger bubble,
Okay.
and then so that's gonna have some buoyant force here, right?
Yes.
And then that's gonna be so you can let's just call that FB. So which is equal to rho air times the volume of the bubbles times
Okay. Yes.
okay. And then you're gonna have
Your gravity. And in
I guess should I draw a direct or?
Yes, no, it's fine. But in the normal case, we would have the bubble moving up since the
But with added mass, this gravity term, so normally gravity is just going to be rho a times the bubble times g, right? So this is just the mass.
Yeah.
So equivalent of the mass.
Yes.
But in this case, you're essentially going to have an added term, which is going to be the added mass.
So we have some water that will move with the bubble, and there will be more water when it tries to move up, and with more water, it will be a higher mass. And it will be harder for the bubble to
Exactly.
move
It's going to
up.
be harder for the bubble to float, which is why the bubble is going
Yeah.
essentially, in the inverse way, it's going to accelerate as it sinks.
Yeah, okay. Then I think we were able to get that.
And my theory does predict.
Yeah, I agree with you. Okay, but now on to the Reynolds number.
Yeah.
So how does Reynolds number change?
So the Reynolds number, so what we did is actually, so drag coefficient is taken to be the time average motion at the maximum speed. So as I showed in the slide, I used the maximum
Okay,
condition,
but don't
which is just A omega squared.
Don't you agree that if you do you have
Or A omega, sorry.
do you agree that the Reynolds number changed throughout
It
the
does
process?
change, however, it's not going to be we're still going to have a quadratic drag.
Okay,
But so as you can see in our equation, it's
I don't
going to
think
fit
every
quite
number's-
well and you can see there's quite good agreement already, and I think this is a fairly small
Okay.
improvement on our model.
Yeah, but I just wonder, I think, if we have our beaker here, and it's moving up and down,
Sure.
yes, then we will have velocity, sometimes it will be going up, and the velocity that will be going down.
Yes.
Yes, so in some point, we will have a velocity that is zero. Do you agree with that?
Yes.
Yes. And if the water's velocity is zero, what Reynolds numbers do we have then?
Well, so also we also have to sorry, but this is what frame are you referring to here?
Well, I'm just in the regular reference frame.
In the regular,
Yeah.
so in the frame of the
Wait.
oscillating container, is it oscillating or not?
Just a regular frame. We're having our
Yes, the oscillation's still there, right?
yeah,
So the bubble.
but do we have a velocity
A
of
time
zero?
of zero?
Yes, somewhere. Yes or no?
No.
Yes, we have.
No, because
Okay. So how
I
does it go from moving this direction to this direction?
because once again, it's the bubble is still going to be moving, is it not? Like relative in a lab frame, it's still going to be moving. Oh, sorry.
Yeah,
Yeah,
but
so-
the velocity won't it be zero sometimes?
Oh,
Is it
okay,
going
yeah,
up?
sorry, I understand what you mean.
Yeah, okay.
Yeah,
It will be zero. And what happens to the Reynolds number when it's zero?
So that's going to be like a very short time, is it not?
Yeah, I agree with
It's
that.
like
but do you
negative,
agree
it's
that the Reynolds number will
It will
become
become-
zero?
Yeah, I do.
Yeah, and does your model actually, can you actually use your model for a Reynolds number that is small?
Sorry, what do you?
Yeah,
so in this-
your drag equation.
Our drag equation functions for so it's
For turbulent flow.
turbulent flow.
Yeah, exactly. But you sometimes have not turbulent flow. Do you agree with that?
In this situation, I think for the most part, as you can see from our model, is that it does fit quite well. So maybe
I agree with that.
perhaps
But
this
do
would
you
be-
agree with
Yeah,
me
yeah.
that-
Perhaps in some
okay, yes.
situations you don't have a turbulent flow, and in that case, yes, we can make improvements to our model. But I still
Okay.
believe it's a fairly
I think we also should discuss how the sinking depth depends on the relevant parameters. So, for instance, if we have a greater bubble with greater volume, how will the sinking depth change? So if we have a graph here, and for instance we have volume here and sinking depth here.
the volume of the bubble.
Yeah, volume of the bubble.
So it's an inverse relationship.
Yeah. So how is this affect?
So
Okay. If it's easier, we can.
I think thinking that
Yeah, okay,
that's
yeah.
gonna be a bit easier.
Yeah. Okay. So volume. What will happen?
So you're gonna see a depth similar to something like that.
Okay.
Similar to that.
Okay. So did you actually test for different volumes?
So for different bubble volumes, the issue is that it's extreme. So with the tube, it's quite difficult to test. We found, and it's again. It's just if we look at actually, if we
I would
look
actually
at
think that it's
It's
not
not
be
very-
that hard. Since
it wouldn't be that hard. However, we found it wouldn't be an extremely interesting variable to analyze either.
Wouldn't you say that
Because
the
it's
size
just
of
it's
the
a simple
bubble is-
parameter in our final equation.
Wouldn't you agree that the size of the bubble isn't interesting?
Sure, it's but you can see that the relationship is fairly.
Yeah, it's very good.
But it's not. I think it's not as interesting to analyze because
Okay.
as you can see with the sinking depth equation, the volume of the bubble is it's located in.
Okay. But you didn't do any experiments on this relationship.
No.
Okay. Should we move on perhaps to the experimental setup?
Sure.
So why did you use a stopper in your experimental setup?
Otherwise, the water is going to come out.
Okay. That was quite clear. Okay. I would also like to use to understand why you only looked at a frequency spectrum from 0 to 100.
So the reason
Isn't it interesting to go even further and see
right,
how theory
but that
works?
was so. Thank you for bringing that up. So one of the reasons for that is actually because of our subwoofer range, which is actually, as a subwoofer is known, you use it for low frequency.
Yeah, but couldn't you have used another
However-
subwoofer that resonated at a high frequency?
So in that case, it's going to. So we only had that one. We were only able to use that one subwoofer,
Okay.
but continue. So with that one subwoofer, and if you were to go past that frequency with the maximum voltage of our signal generator, we would not be able to generate that same amplitude. So it's just a limitation of the equipment.
Okay, but do you agree with me that it would be
Yeah, it would
interesting?
definitely be interesting.
to look
However,
at-
just with the limitations of our experimental setup, it's quite difficult.
Because if you look at a broader frequency spectrum,
So
we
if
have
we
your
increase the
data here, but we haven't looked at
frequency,
it.
you're going to have a much lower amplitude.
Yeah, I agree with that.
Yeah,
but the
so-
acceleration can be still be high since.
Yeah, but we don't want to vary two parameters at once, right? So we want to because
No, but
if you increase the frequency of a subwoofer, the amplitude will decrease.
yeah, but you could have used a speaker that is rated for a higher frequency, which is able to produce a high acceleration at that frequency.
And at that point, the amplitude becomes very different
Yeah,
because it's very small.
But don't you agree from your models that the important thing is the amplitude times omega squared?
Sure.
Yeah. So if we increase the frequency and square, even though if the amplitude goes down, it still will be able to work. Don't you agree with that?
I agree that it'll still be able to work. However, we're not going to be able to measure the amplitude because it's going to be too small.
Okay.
At those high, let's say 300
But
hertz. the
will we
amplitude
see the
is
sinking occur?
At certain conditions, for sure, we'll still see the sinking occur. As you saw in my my first graph that I showed of the, you can
Because I think you should have checked for higher frequencies. Yes. Yes, so we began by talking about why the bubbles sink, and I think we came to a conclusion where me and the reporter agree that the most important thing in this diagram is in fact the added mass, and that the added mass changes with the volume. So when the bubble is up here, it will have harder to move upwards than downwards, and this is why we don't see the phenomenon occurring normally. So when the oscillation and the difference in oscillation is high enough, we will have the volume be high enough in order for it to move downwards. Then we discussed the Reynolds number, and I think we came to a conclusion that the Reynolds number will change during this process, and we have a point where the Reynolds number is 0. And I agree with the reporter that his model for modeling for the drag of the bubble is correct for turbulent flow, but since we have a non-turbulent flow and laminar flow during the process, when the velocity is very low, we will be able to we can't use this type of formula.
So, would you please connect your computer to? Oh, yes. So, thank the reporter and opponent for this constructive discussion. So, let's proceed with the question. First, the reporter, do you use distilled water or was it salted? What kind of
Water is used, just standard water.
The standard water?
Yeah.
Not purified, not distilled, nothing.
No, it's not necessary.
It doesn't matter.
Yeah.
It could matter. Okay. So slide 13.
Slide 13.
Yeah. Sure.
Yes.
Why is it described with a simple harmonic oscillation equation?
Since it's a simple harmonic motion, it's due to the receiver. It
What?
provides the oscillation.
And how do you extrapolate that? How are you sure that?
As I discussed earlier with the opponent, I said for my amplitude measurements, you notice a sinusoidal curve.
Number 15. How do you extrapolate this equation and specifically the omega square? Here. The omega square. Yeah. How do you?
Which omega square? Oh, by taking two derivatives. So a sine omega t is going to be how you characterize your simple harmonic motion, and then you take the second derivative and you'll get an omega square.
Okay, number 26 slide. Yes. Here, what's the Z factor?
Sorry?
How do you find the G factor, the gamma factor?
Gamma factor.
Yeah.
The gamma factor is just a constant just to reduce clutter in the equation. Otherwise, it's even more messy.
To the reported opponent, is Reynolds number dimensionless?
Yes,
Yes.
it's the definition.
When it's more turbulent the flow of the fluid, a high Reynolds number or low Reynolds number?
Low.
Low? No.
What was your question?
Low Reynolds numbers.
Do you agree with the reporter?
Could you restate
Low
the
Reynolds
question?
number for laminar flow.
For
Yeah.
turbulent.
Oh, for turbulent, greater than 2300.
Yeah, high or low.
So a low Reynolds number will mean laminar flow.
A higher Reynolds number is turbulent.
Yeah.
So high, because you said low. Of which ratio is the Reynolds numbers? How is it defined?
You mean by my equation? So the rho times the v times L divided by mu naught.
Yeah, it's because
I times e to the 12th or
problem description, when a container of liquid, such as water, oscillates vertically, it is possible that bubbles in the liquid move downwards instead of right. Now, about the reporter, his strengths, there was a fun analysis of the experimental setup, including visual footage, has used a computational program, Python code. Third, clear separation between the individual parts of the presentation. Fourth, analytic graphs were used to present the results like error bars, theoretical lines. 5, including the references from which the theoretical model was formed. Now, there are also some weaknesses. There was poor explanation of the mathematical formulas and the conclusions that were made from them. 2, unclear qualitative force analysis, since it was focused on differential equations rather than physical explanation. There was also poor time management, spent 2/3 of the presentation with a theoretical analysis. And also, and 4, not all of the experimental results were used, size of bubbles, temperature. And 5, rejected some of the opponent's proposal, used a speaker for our frequency. Opponent. His strengths, explicit summary of the opponent's presentation. The opponent team is very attentive, asks specific clarifying questions to the reporter. Good knowledge of the theory behind the phenomena. 4, examine main parameters and try to test the reviewer in many forms, such as volume of bubble, flow, Reynolds number. 5, proposed a way to examine the effect of the volume. And about the weaknesses also, the opposition team focused on the theoretical model without questioning the numerical equations, the derivatives, the integrations that were used by the reporter. 2, did not examine the experimental setup or the experimental results. 3, there was poor time management, focused too much on a single thing, forces. Class point. Opponent, does any Reynolds number change? Reporter, yes, but slightly, as an invisible effect. Our opinion, we agree with the opponent, since it does have zero velocity. Class point. Second, opponent, we will increase the frequency. Is it worth it? Reporter, no, because the amplitude will be too small. Our opinion, it will be interesting to peak a few measurements to see what happens. And our conclusion now. The reporting team should have considered some factors in order to convince us of the completeness of the experiment. For example, he explained about the brown dots in slide 32. Why is it exponentially graphed? What was the numerical error? Second, the reporting team should have experimented with higher frequencies. Third, generally both sides had a good understanding of the physics behind the experiment and the discussion was fruitful. 4, there would be more visual footage of the experiment. And 5, most important factor is the added masses. And lastly, there will be more explanation with regards to graphs and the mathematical type of F drive. That wasn't explained. Thank you very much.
I'd like to thank the reviewer and the opponent for their comments and concerns. And so first, I'd like to go over some of the points raised throughout the discussions. So first, I believe the opponent brought up some error in numerical solution. So I'd just like to clarify that it uses the run kata as well as a small time step, which means that the error is going to be fairly small in terms of the numerical solution. Next, so in terms of the deviation near the end of the motion, which the opponent did point out briefly, is that this can be due to the regular flow near the bottom of the container, which can be extremely difficult to predict. Next, in terms of testing higher frequencies, which both the reviewer and the opponent brought up, we can, as I stated previously, it's fairly difficult to measure these higher frequencies because we wanted to keep amplitude constant. And it's going to be extremely difficult to measure these very, very small amplitudes at current frequencies, say at like 200 hertz. And in terms of the drag coefficient as a function of the Reynolds number, which is a function of my velocity, I agree with the opponent that this perhaps would be a more accurate model. However, the current model fits quite well, and if we were to calculate the Reynolds number, it's going to be for very very small periods of time, which is why, as you can see, my theory over here in the top right actually still fits quite well. And so in conclusion, I'd just like to restate that we tested this phenomenon using a very well-controlled experimental setup that accounted for frequency, initial bubble height, initial bubble size, as well as the amplitude of the oscillation. Then we varied several key parameters with the experimental verification, and you can see that all the trends have the correlation. And in that sense, we believe that we have solved this problem of sinking bubbles quite effectively.
Question comes from Gerald.
Okay, so you say that the Raymond number is turbulent in the system. I'd like to ask, in the theory, especially the added mass section, is there any assumption when you have the flow you know about? Did you read about the other assumptions made out in the paper?
So added mass, I don't believe that's necessarily dependent on the turbulent flow. I think that's
So
mostly.
it works with laminar or turbulent or both?
I believe it should.
Yes, sir?
Both.
Okay, and I have another question. Is it okay? So you said that you didn't vary the radius of the bubbles, the volume. So what volume did you use?
So I rendered the radius of my bubbles, which was, as I stated, was 2.8 millimeters.
2.8 meters. And why didn't you change the radius?
We attached it to a pump that was pumping bubbles slowly, and we only really had one size of like the inner tube that I showed in my setup that really worked.
And do you think the flow would be more turbulent or less turbulent if you increase the volume of the bubbles?
So the flow would be more turbulent since my characteristic might increase.
What does the review recommend?
When it's higher, when it's more high, the Reynolds number, it's more turbulent. If it's low, it's more laminar.
Okay, elbow.
Yeah, I agree.
Good.
With the reporter as well.
Okay.
I have a question for the reporter. What's the role of the liquid in this case? Why do you have to have a bubble rising liquid?
So added
Would
mass
it
will
happen
only
in the air?
occur in the air. Added mass will occur in the fluids, but in the air, it's more significant in a liquid as the density of the liquids is going to be much more greater. And
My point is that the water is there to provide variation in pressure.
Sorry?
The water is there to provide variation in pressure.
Yes, that's also true.
You also investigate the motion of the water inside the bubble or inside the bottle itself.
So
Is it stationary or?
for the most part, so we filled up. Obviously there's still some movement, but we filled up the container to essentially full, or almost full.
But there's still some movement, right?
There's still going to be some movement which we didn't consider, which could perhaps explain some of the deviations there.
Any other?
Can I ask a question? In your modeling, you've got the added mass as a sphere around your bubble.
Right.
May I ask why?
This
You're
is
talking about something moving through the fluid and you're getting a layer of fluid.
right. So I drew it as that's simply just like a visualization of the added mass. So added mass is really just like an imaginary concept to illustrate how it requires extra energy to move the fluid around the bubble. I just illustrate as that just to kind of demonstrate how it would, like, in a more intuitive way.
Well, I have one question about the added mass. Can you please show the formula for this added mass? Yes. Okay. So you said that for a sphere, this coefficient heat is equal to 1/2.
Yes.
Why?
So this is derived by literature from a most.
And doesn't it depend on the speed of the bubble?
It depends. So I think I tried. So my theory is based on the assumption that the bubble stays spherical. Which as I stated later, I think the bubble will be compressed. Sorry.
How big your bubbles are?
2.8 millimeters. Quite small.
So you also had some Python simulation as well as some theoretical prediction, just like some analytic solution. Why?
So I wanted to show that for the Python simulation that because with just the critical length you can't visualize the
Oh, so
trajectory.
you're-
So I use the Python
yeah.
to simulate the trajectory of the bubbles, essentially. Trajectory in 1D.
Sure, okay.
I have more questions.
For the opponent, if I increase the volume of the bubble,
Yes.
do you think this shape would be less spherical or more spherical?
Well, I think the pressure gradient inside the bubble will deform the bubble a bit.
Uh-huh.
Yes.
So should the theory deviate more or less for well,
I think it will deviate more.
and what do you think?
So for the chi value would increase because it's going to become so it's essentially more cylindrical. So yes, it would.
Okay.
Right, thank you.